Going to look at trig substitutions. Mentioned the idea before, but it's where we've got this square root and we've got the squares there. And so we try and combine them using a trig identity into one term rather than having two terms. So if you see a squared plus x squared, then use a tan theta, because then that will become a squared plus a squared tan squared, which is a squared sec squared. You get it down to 1, square root of that, a sec theta. If you see a squared minus x squared, well, you've got a choice. Either a sine theta, a cos theta. And if it's x squared minus a squared, that's where I'll use sec, because we'll get sec squared minus 1 is tan squared. So we can bring them all back. So let's look at a few examples. Now, this is actually one of our standard integrals, but let's do it via the substitution to prove what it is. So we've got a squared plus x squared. I'm going to use a tan theta, which means dx is a sec squared theta to theta. Let's sub it all in. So on the top, a sec squared theta to theta, square root of a squared plus a squared tan squared, which is a squared sec squared, which is a sec. So I'm saying a sec squared divided by a sec, so I'm left with just sec theta. The integral of sec theta, which you recall is the log of sec plus tan. But how do we get x back in there? Well, we draw ourselves up a little triangle, because when we've said x is a tan theta, another way of saying that is tan theta is x on a. So in our triangle, I can go, well, opposite is x, adjacent is a. Magically, the third side is the square root we've been dealing with. Well, I say magic, it'll work every time. It's the whole point of doing it this way. So now I can just read off that. So sec is the square root of a squared plus x squared over a. Tan is x on a. But you might recall I said that it's going to be the log of x plus the square root. It didn't have over a. And this is why. I can use my log laws and say, well, that's the same as minus log a. But log a would be a constant. So it is the same thing, it's just the constant is a different constant. And it just looks neater without having the a on the bottom. So with the one that we memorised for that integral, we don't worry about the a on the bottom. We just say, well, it's the log of x plus the square root of a squared plus x squared. But there's the proof of how we get it. Again, here's one where I'm not suggesting that the trig substitution is the best way of doing this, because hopefully you're looking at that and saying, well, hang on, we can just create derivative over the function there. But let's do it by a trig substitution. In this case, I'm going to use x equals sine theta. So dx is cos theta to theta. And so on the top, I get sine theta times cos theta to theta. The bottom, we've got square root of 1 minus sine squared, which is cos squared. And the square root of cos squared is cos. So when we divide that into the top, I'm now just integrating sine theta to theta. Integrate sine, we get minus cos. Need to get x back in there. Let's draw up our triangle. In this case, the ratio is x over 1. The third side, oh look, there's that square root. It matches again. So we read off that cosine and we get minus the square root of 1 minus x squared plus c. As I say, much quicker if you notice the derivative on the top, because then we've got that standard du on root u, which we know is 2 root u, and bang, there's the answer. But it's certainly a way of doing that particular integral. Did I do a third one? Yes, I did. Okay, square root of x squared plus 3. So this one I'll do root 3 tan theta. So dx is root 3 sec squared theta. We've got root 3 sec theta. The square root of x squared plus 3 becomes 3 tan squared plus 3, which is the square root of 3 sec squared, which is root 3 sec. Multiplies together, we've got 3. The integral is sec cubed. Oh, sec cubed. That's the one we love because we've got to do it by parts. We split it up into sec and sec squared. U will be sec. Du is sec theta tan theta to theta. Dv is sec squared. V is tan theta. But remember, it's 3 times the integral here. So it's 3 times uv. So 3 sec theta tan theta minus 3 v du. And so that's 3 sec theta tan squared theta. But now the tan squared we can change to be, it's sec squared minus 1, but it's minus 3 times that. So we get minus 3 times the integral of sec cubed theta plus 3 sec theta. Let's just integrate the sec theta, and that's the log of sec plus tan. Now I'm going to substitute back in. Draw up the triangle. Hypotenuse. Oh, look, it's the square root. Okay, we can substitute back in now, but have a look at what I've done. This is where we've got to be careful. 3 sec cubed theta, there it is, the third line, is equal to the integral of x squared plus 3. So I can sub in the integral of x squared plus 3 for that 3 sec cubed theta. So I sub that in. And the other substitutions. But now we read it like an equation. I can move this square root of x squared plus 3 dx to the left-hand side, and we end up with 2 lots of the integral of x squared plus 3 is this wonderful expression here. Divide everything by 2. I mean, that's good enough for an answer. I just don't like the root 3. I mean, I'm going to get rid of it. And I can just get rid of it because it would be log of root 3, which is a constant number anyway. Don't get hung up in that I've still used c and c. Yes, those c's are different c's, but I'm just saying it's a constant number. It doesn't matter. So look at that. Oh, wow. What a great question that one is, isn't it? All right, so I say, in the sheets, I've put in an old Patel exercise to have a go at some trig substitutions there.